So today we are very glad to have our guest speaker, Dr. Jidong from the, actually he's an alumnus from USF, and he's currently an associate professor in civil engineering at the University of Georgia. So today we also have some students, actually some people from the University of Georgia attending this seminar. So this seminar series is organized by the Department of Civil and Environmental Engineering at the University of South Florida, and also co-organized by the Center for Urban Transportation Research at the USF. And I'm an associate professor in the Department of Civil and Environmental Engineering. And I also want to mention that this seminar series is also co-sponsored by the USF student chapter of the Institute of Transportation Engineers and the USF Women in Transportation Society, and also co-sponsored by 3 university transportation centers, including the Center for Transportation, Environment, and Community Health, and the National Institute for Congestion Reduction, and the Center for Teaching Old Models, New Tricks. So CTEC, NICA, and TomNet. Let me give you a little bit of introduction about our guest speaker. So he's Dr. Jidong Yang, actually. We've been knowing each other for quite a while, and he's a USF alumnus. He graduated from USF from our department, the Department of Civil and Environmental Engineering, with a Ph.D. degree, and he has extensive experience in both industry and government agency and academia. And now he's currently an associate professor in civil engineering at the University of Georgia. And he's also a registered professional engineer. And his current research has been heavily focusing on the artificial intelligence, and particularly the deep learning methods and the applications of the deep learning methods in transportation engineering, like in ITS, highway design, safety, and sustainable and resilient infrastructure systems. So today his topic will be the self-supervised deep learning framework for anomaly detection in traffic data. So without much further ado, Dr. Yang, the floor is yours.
Okay, sure. All right. Thank you, Dr. Lu, for a nice introduction. Glad to be kind of speaking to the USF students since I, originally graduated there. So, so today's topic is going to be self-supervised deep learning regarding kind of a anomaly detection for traffic data. Okay, here the outline for my today's talk. First, I want to touch a little bit on the background of the project we're doing for this research, and then followed by the data acquisition and the fusion, because we're doing the data, analytics. So the data acquisition and the fusion will be a big part of that. And then after that, we can talk about what kind of model we developed for QC, quality control of the traffic data. And basically, there are kind of two categories of the model. One is the called VAE-based model. VAE is a variational autoencoder, a very kind of a commonly used self-supervised learning model. So that model captures kind of any anomaly occurred on a daily basis, a full day kind of window. Another type of model, we use a recurrent model, which targeting a smaller kind of an incremental, more like a rolling window. So we're looking for 5 million traffic count, see whether there are any anomaly or not. Okay, but the two-type model give you kind of a two-time scale, right, in terms of inspecting the data. And finally, you're going to show the result, how model perform, and we also develop a web application for the model, so the DOT can use that for their convenience for data quality control. Okay, first let's talk about the product background. So the reason why we do this thing, right? Why we do this research. Everybody, you probably all know that high quality traffic data is a foundation for a lot of things, right? For planning, engineering, for example, for bridge and pavement design. So you need traffic data, classification data, right? So in generally, it's been used for decision making for any big investment for infrastructure. So another big part of the collecting high quality traffic data would be generating the annual HPMS report, which is required by the Federal Highway Administration. Okay. So the current status is this: for quality control, the State Department typically utilize the rule-based procedure for review the raw data. So typically they use a kind of an automated system to kind of to check the data, whether there are any anomalies, and then they can screen it out or make some correction if needed. So here's the GDOT process. So this is, by the way, this research, I forgot to mention at the beginning, it's funded by the Georgia Department of Transportation. So we'll try to kind of improve the GDOT data QC process here. So I just want to give you a brief review on what's currently in place at GDOT in terms of data QC. So this kind of a flow. First, you need to collect data, and you need to review and QC incoming data from the sensor directly, right? That's your raw data. And then you decide whether you're going to accept or reject or maybe recollect the data. And then you store the data for reporting, for any other purpose, okay? So here we're targeting the second step here. We're going to review, which is the review and QC incoming data. So on your right-hand side here, the big table basically is some kind of criteria currently being using by GDOT. It's just kind of a, the checklist, whether the data, are normal or not based on those, criteria. So which you can think of is very kind of subjective, and a lot of criteria is very insensitive to the true anomaly data. So make the process is not very robust to identify the true anomaly. So here, the idea for this research is that, since we have a lot of different sources of data available, why can we leverage multi-source data for improving the QC process? So here, the two typical data, traffic data collected within a DOT would be kind of a two sources of data. One is for the CCS station. So even though this is for this research done for the Georgia DOT, but the same concept applies to any state DOT. Typically, those two sources of data have been collected for pretty much all the state DOT across the U.S. So on the left-hand side here, you can see there's a CCS station. CCS means continuous count station, which collected by inductive loop technology, which is very kind of reliable, because you have the loop cut right on the pavement surface. So that's kind of traditional technology being used for data collection. On the right hand side, you see the small kind of gray icon. That's kind of camera. We got a lot of camera cover the interstate road. So in Georgia here, you can see on the left hand side, we got roughly 250 plus CCS station statewide. And on the right-hand side, we got more than 1,300 VDS station. VDS means video detection system. So each station, basically the camera. So the camera can do the count as well. So we got much more VDS station than the CCS station. But typically, the DOT uses the CCS station for planning and engineering purpose, because they are more kind of reliable. Okay, so the thought is this: how can we just leverage both sources for improving the data quality? So basically, we try to cross-checking the data source from each other. So that's kind of the idea here. So the purpose here, we try to develop some kind of robust QC procedure for this research by leveraging multi-source data. Okay, so to be able to cross-checking, one source from the other, so we need to kind of match them, right? So we need to match the location. So there's some challenge in doing that, because the VDS station here, they're looking at the targeting unidirectional traffic, which means the collect directional traffic volume, but the CCS station collecting two-way volume, both direction. Okay, so basically, typically when we match them by location, by some other kind of feature, so typically you have more than one VDS station to match to a CCS station. The red marker indicating the CCS station, the blue marker indicating the VDS station. Okay, so you can see upper right corner here, we got 3 VDS station matched to a single CCS station. Typically, you got 2 directional, right? You got 2 kind of blue matching the unidirectional blue matching the 2 directional right, and sometimes you got the adjacent one, which means the upstream, downstream, they're very close to each other. So typically, we got 3 kind of a VDS station matched to a CCS station. So the matching process is kind of a really time-consuming process, as you can tell here. So we rely on kind of 3 different things to make sure we match to the true, station, meaning what both type of station monitor exactly the same location. So we use the geospatial distance, and then we also use the on-road travel distance, and also some kind of description we extracting from count. Okay, you can see the description here on the upper right. Okay, an example here, you look at the bottom right, we try to match one of the station here, which is the in red marker, to a nearby station. So you see the one a little bit to the north there, there's the kind of a small circle there, that's another station. Basically, if you based on the distance only, this 2 is the most close one. So you match the one to the other, right? But in fact, they're monitoring different roadway. So that's apparently wrong, right? So that's why we use the on-road travel distance. Basically, we leverage the Google API, Google Map API, to compute the travel distance from one station to another, and to determine whether they're on the same route or not. So by doing that, we'll be able to match correctly those stations. Here's some kind of example, after we match it. So this is one of the location. Different color here, let's see, the blue indicating the CCS station, the red indicating VDS station. As you can tell, they're following very similar trend, right? Sometimes the VDS station is not very stable. You can see the bottom one, we got big drop there, because the video detection system largely affected by the weather condition, right? That could be caused by, that big drop could be caused by some kind of weather condition. So in generally, they're matched pretty well. And also in generally, your VDS count kind of a little bit lower than the CCS count, because the nature of the video detection system. But the good thing about this is they follow the same trend. So that's kind of feature we're looking at for QC purpose. So next, I'm going to talk about the model. So there are 2 type of model we talked about earlier. The targeting 2 different time scale. So one is the VAE based model, with targeting the whole day. We look at kind of pattern on a whole day base. And for that model, we try to extracting feature using different transformation of the original signal, such as the wavelet or recurrent plot. And then we use the VAE model to kind of take those transformation and embed them to a kind of low dimensional, high level feature space. And then we're going to exploit the latent space to detect the anomaly. So I'm going to talk about the detail later on here. So another category of model would be, we call it real time, but it's not real time, right? Basically, it's nearly to the real time, because we looking at every 5-minute interval. So typically the count, we do a 5-minute count, right? So we're looking every 5-minute interval to see if there any kind of anomaly we can detect. So there are different categories of the model we evaluated for this real-time model. including recurrent network and long-short LSTM, and the gated recurrent unit, GRU, and the most recent one, the liquid time constant network, which is the LTC. So let's look at the VAE model first. So we did two kind of a transformation, transform the original time sequence signal into some kind of a image, a plot here. So this one shows the recurrent plot. So you can see on the right-hand side the dynamic, right? So when the signal change, your plots change accordingly. You can see the pattern. So this the recurrent plot tries to capture the dynamic kind of a system at what kind of phase the system kind of recurring again. So that gives you kind of a very distinct pattern. For example, this kind of plot can easily identify if you have a chunk of the data missing, it can easily identify that. Okay, that's very kind of striking feature in the recurrent plot. So another, let's see here give you some example here. So on the left side we have the traffic data scaled, and then we transform it using recurrent plot, and then we reconstruct it by the VAE. So we're going to talk about the VAE model later. But the VAE, basically, you get the input, you try to reconstruct it at output, right? So you can see the reconstruction result is pretty good. It's almost identical. So another transformation we use is a wavelet. Wavelet basically, you can easily understand that on the by looking at the animation on the right-hand side here, right? So basically, we have the mother wavelet, and then you kind of scan that through your signal, right? And then you're extracting different kind of frequency information. So you can see the wavelet plot at the bottom right here, right? Again, you can see the pattern change depending on your input signal there, right? It captures both kind of high frequency and low frequency, or different frequency level. Again, it casted into a kind of image here. So we also kind of develop a VAE model for this wavelet based on the wavelet image here. Okay. So here's the result. So you got traffic data scaled and transformed based on the wavelet plot, and then you reconstruct it. So you can see here reconstruction a little bit different than the one you saw before for the recurrent plot. But this one, basically, we try to kind of reduce computation cost. But at least you can see the pattern is very similar. The large scale pattern rather than the kind of, the pixel wise kind of different. So that's basically what we want. We want the model to generalize, to look at the pattern rather than look at the kind of tiny pixel detail. Okay, so what is the VAE here? So I bet most of you probably know this if you do the research with deep learning. So you got the input here. We get input image here. For example, I just took the recurrent plot. We get the model for both recurrent plot and the wavelet plot. Okay. So basically, you extracting feature from the image, right? And a different level, and then you kind of this is called the encoder. So you project into a lower dimension space. Basically, you reducing a spatial dimension, you're increasing your feature dimension, which is the depth dimension here. And then you basically try to compress everything into a kind of a low dimensional latent space. We call the phi here. And that's kind of bottleneck. From there, you can reconstruct whatever your image is. So we got encoder and we got decoder. Typically, encoder, decoder take kind of a similar kind of symmetrical structure, but that you don't have to do that. In our research, decoder you can make a decoder much simpler than the encoder. Okay. So how are we going to identify the anomaly based on this model here? Basically, once we kind of train the model to be able to reconstruct the image. And then we look at the latent space, which is low dimension, right? So we want to see if the data point, if anomaly or not. We're going to look at his location of that data point in that low dimensional latent space. Okay, so here, could just show you, how the VAE work here. This from the original paper of the VAE. So you look at on the right hand side, it's kind of 110 digit, which is the MNIST data set. So they just train the model to reconstruct those kind of 110 digit image, right, using the VAE. And then the Z here, Z indicating the latent space. Let's see, let's just pick a 2Z, 2-dimension, right, from the latent space, which is Z1, Z2. So you can see by varying Z, so you can reconstruct image at kind of a very well in terms of the digit morph from one to the other, right, smoothly. So this can be thought of as a kind of a manifold in the latent space. That's what the VAE try to get at, right? We try to generate kind of capture the data manifold in the low dimension space, because we all know the image, natural image, live on the kind of a low dimensional space. So on the left-hand side here is another kind of application, which the human face data. So after train the model, you can see here we got 2-dimension just for viewing purpose. So we got Z1, Z2. You can tell here kind of Z1 capture the head pose by varying Z1 in the Z1 dimension, right? And the Z2 dimension capture the degree of smile. Okay. So what's those kind of head pose and degree smile? Those kind of a high-level feature we try to kind of capture, right? So that's kind of embedded in your latent space. So we try to do the similar thing with our data. So this kind of a model structure we finally fine-tuned, which work well. So on the top one we got the wavelet model. On the bottom one we got recurrent plot model. So here's the kind of framework, the pipeline we do the anomaly detection based on the VAE model. So once we train the VAE model, we kind of take the decoder. We kind of throw out the decoder. I'm sorry. We take the encoder only. So we got the input data here. Let's say we got our kind of a time sequence for a whole day. So we transform them to the recurrent plot, which is on the top, and also wavelet plot at the bottom. And then we pass them through the encoder, right? So we got the latent space from both, and then we concatenate them together, which is the Z, which is the latent space, right here. So what we use latent space dimension 64. 32 come from the recurrent plot, 32 come from the wavelet. And then that's kind of 64 dimension latent space, which is much smaller than the original space at the 2 image. And then here, with all the data we train the model, right? So basically those data are going to be form some kind of the manifold, data manifold in the latent space, right? That's in that 64 dimension, low dimensional latent space. And then let's say if we want to take a new data point, test data point, we want to see whether that data point is anomalous or not, right? So what we can do here, we can project that data point, which is the xi here, to this latent space. And then we're going to see how far away that data point from your underlying manifold, right? So, but to compute the distance from that testing data point to the underlying manifold, which is a kind of a nonlinear surface, would be very difficult, right? So what we propose is that we can choose kind of form a hyperplane, so to speak, to approximating the manifold at the point that's close to that data point. So we can compute distance from data point to the hyperplane much easier. So the hyperplane here is going to be in even lower dimension than this latent space, right? So what we did here, we did this. We take the test data point, we find the nearest neighbor, we call the KNN, K nearest neighbor. In this case, k equal to 64, which is the same dimension as your latent space. And then once we find the k nearest neighbor, we can do the PCA projection. So the PCA basically gives you the hyperplane, right? So we take the 64, the k nearest neighbor, and then we kind of project to a PCA space. In this case, PCA space is going to be, in our case, 20 dimension, which is a lower dimensional hyperplane, right? So the 20 dimension, why we use the 20 dimension here? Because the 20 dimension give us more than 90% of the variance explained by the PCA. And then we look at the data point in this latent space, right? We can compute the distance from the data point to the hyperplane very easily. So here, the three types of distance being calculated. You can see on the right, upper right, we got different color: blue, red, and green. So basically, we project the data point from both sources, from VTS and CCS here. So the distance from those two data points to the hyperplane we can compute easily, and also we can compute the distance between those data points, right? So here, kind of result here to show you. So let's say we take a one location, right? So we got the CCS. You can see the image here. So top row is the original image. The bottom row is the reconstructed image from the VAE. You can see they're pretty consistent, right? So that indicating, let's see, not only that, if we compute the three distance, which is color coded, right? The green, blue, and red. The distance we computed here is shown at 3.4, 2.5, 2.9. Those numbers are relatively low. So this indicating your data point is close to the manifold. Also, your two data points close to each other, which means they're similar, right? So that's indicating the data point is normal, okay? So there's another example here. You can see on the top that original image, at the bottom is reconstructed. You see the reconstructed image is pretty bad, right? Especially for the recurrent plot there. This indicating basically anomaly data point. As you can tell, the number computed for the distance here, we got 5.08, which is pretty large, which is the green, meaning the CCS data is further away from the underlying manifold. So so is the VDS. We got 4.8, also pretty large. But the distance between the two data points are pretty close, which is 1.49. Meaning what? Even though they both both data look kind of anomalous, but they're close to each other, meaning what, they're very similar. So this we kind of capture this as an organic anomaly. Organic, so to speak, maybe something related to the non-recurring event. For example, incident on the freeway, it got congestion. Traffic count is going to be abnormal because of that. But that doesn't mean your count is true abnormal because it's altered by the actual event, right? So we'll call this a kind of organic anomaly. Okay. So true anomaly is this. So you look at the plot again here. So the reconstruction on the recurrent plot is not that bad, right? But reconstruction on the wavelet is not that good. You can see here the detail it's much different here. So look at the distance here. We got green, blue, and red here, right? You see the number pretty large. So it's all kind of more than 5. And for the cross distance, which is the red one, it's 10.96, meaning what, they're very different. So this tells us, the data most likely going to be true anomaly. Okay, that captures kind of full day model we use for the VAE. So next, we're going to quickly go through some kind of a recurrent model. The recurrent model kind of much easier than the daily model. because we don't need to do any kind of a transformation here. So this kind of model we tested for different type of model: RNN, GRU, LSTM, and LTC. So here's the structure we adopted for each type of model. So behind this, we get a lot of fine tuning going on to testing which structure would be better. So on the left hand side here, this kind of show this plot capture 3 type of model: RNN, GRU, and LSTM. N here, capital N indicating number of the recurrent module, meaning what number of layer we use. We use the 7 layer for RNN, 6 layer for GRU, 4 layer for LSTM. And we also use the kind of dropout layer we added to drop out some kind of hidden neuron. So we use 20% dropout rate. That's kind of proved to be working much better than without dropout. On the right-hand side, we use the LTC model, which basically take input and output. Basically, we take the input as a kind of string of the time sequence data or traffic count, and then we just predict the next interval. That's your output. You can tell here we have different color here indicating different type of neuron used for this LTC model. So LTC model basically is a kind of ODE model, neural ODE based model. So here we use different wiring. We use a kind of a fully connected wiring and also NCP wiring. NCP is a neural circuit policy wiring, which reduce the number of connection there, make your kind of make network much faster than fully connected, but still give you very good performance. So next, let's go through some kind of result, how our model perform here. So for evaluating model, we have to have kind of some kind of benchmark, right? So we have to have true anomaly. Unfortunately, we don't have much true anomaly data we can get from the original data. So what we did, we created an artificial anomaly based on the observed error pattern. So here, what we did, we decreased volume at random time interval by 30%, indicated by the plot on the right-hand side here. You see the big dip here. That's kind of the error we injected into the original time sequence. Another type of error, basically, we try to reduce consecutive interval by some amount, in this case by 30%. So you can tell here the big job flattening out here. That's kind of a 30% reduction for a window, for a small window. So another type would be we just zero out a big chunk of that. Okay, those 3 types of error, we created. Basically, those type of error try to replicate what we see in the real, real data. Okay, here's the result. So for the VAE-based model, this kind of confusion matrix with some kind of, the metric we reported here, including the precision, recall, and F1 score. So you can look at the F1 score here. We got 0.94. It's pretty good in terms of the model performance. And this for the recurrent model. On the left-hand side, we compare the different kind of model structure here. You can tell here the LTC fully connected structure give you the best performance in terms of the error. Also, that give you also LTC model have much less number of parameters, as you can tell on the last column here. So on the right-hand side, it's just a kind of classification result. So in this case, we got F1 at 0.85. It's not as good as the full day model. It's kind of understandable because you're looking for the next time step, right? And then you're looking for whatever historical information you can gather. That information, that contact information is much limited than the full day model, right? Full day model, we basically look at the whole day. We can extracting different signal from the whole day, and then we can easily detect if there's an anomaly or not. But But anyway, even though our recurrent model have a little bit worse performance, but still work relatively well. Okay, finally, so to help the GDOT to implement the model results, so we developed some kind of an application here. Let's show the interface here. So you can tell here, you show not only the true count and the model prediction go with each other on the top here. The middle one here try to identify those kind of anomaly data point, and also we pull in the weather condition as well, which is the third chart on the right. So that's indicating, if there are any kind of severe weather going on, that may kind of affecting the count. So also, we can check the, reconstructed plot here to see, to easily see whether it's really anomaly or not. Okay, I think that concludes my presentation today. So hope you enjoy it. If there are any questions, I can answer here.
Thank you, Dr. Yang. A very nice, neat presentation and containing a lot of information. So let's take a look see if there's any questions from the audience. If anyone had any question, you can just unmute yourself and just ask the question. Dr. Yang, maybe I can just ask you a few questions.
Yeah, go ahead.
How many data were used in training actually for the model and that was implemented on the web?
We used 2 years data, the past 2 years, and also given the number of count station, we got a lot of data. If you think about the full day model,
right.
2 years data plus times at least 250 station, that give you a lot of data.
And
yeah, but yeah, I think to answer the question here, you can tell I think this kind of even though this test data set, this how much kind of we use 1,000 day for the testing purpose, but for training we use much more than that. I think more than 10 times of this.
So at the beginning of your presentation, you mentioned that the matching of the two data sources.
Yeah.
Matching of the location from the 2 data sources was done automatically. So did your team actually do some manual check about the matching, the goodness of matching of the?
We did this. Yeah, we did this automatically, but we still kind of QC a little bit after that. As the QC doesn't catch much error. Basically, it's just the automatic process. Did a pretty good job. The reason for that is this, because we use Google API, Google Map API, so we can find out whether the two count station kind of monitoring the same location is on the same road, right? And also whether the upstream or downstream. So by doing that, we'll be able to get very accurate matching. So basically, every time we try to find whether a station matched to this or not, matched to another station or not, we call the Google API map. We compute distance, see which road they are on, right? Whether they're travel the distance between the station, whether it's on the same road or not. So.
Now another question I have is do you have a definition about the anomaly, in your web application, or you just visually show the difference between the expected traffic pattern and the pattern?
Their definition of anomaly basically, it's hard to tell,
Right. Yeah.
You have to especially the true anomaly is hard to tell, but the organic anomaly is easy to tell. But those anomalies basically not really what we want to get, right? Because they're affected by other events. So it's not you're not caused by the sensor malfunction. So it's kind of a little bit challenging, but that's why we create an artificial anomaly here. We don't have much anomaly data. We have a few, but we just try to kind of emulate the pattern by artificially injecting the error. That way we can evaluate our model. So, but one anomaly very obvious, which is the zero out anomaly. Basically, the most of the time the sensor just not responding. They're not counting anymore. So, it kind of they sleep for a while and then come back again. But that type of anomaly would be very easy to identify. Yeah.
Yeah. So that's actually that's what I try to ask. Like from the application perspective, by like Georgia DOT, probably they are more interested in detecting the real-time anomaly, like the down of the sensor. And so I believe they should have some measures in place, like implemented in place to perform the QC of the real-time data.
Yeah, typically it's not. There are no. They don't have a person now to looking at those, right? They rely on the autonomous, detection system. Right. But right now, I think the autonomous detection system basically just try to capture try to do the QC process, kind of batch processing. It's not just in real time. So it's not looking at every 5 minutes or every minute. Yeah. But this process helps GDOT to kind of screen out the true anomaly data, and then they can archive the data for their planning and engineering purpose. For the real time, I think it still gives some kind of insightful information for the real time detection. That, for example, if the sensor have a malfunction now, right? So if they catch that in real time, they'd be able to send people out there to fix it. Yeah, in a more kind of timely manner.
And due to like a better communication between the sensor and the office.
Yeah, could be. Yeah, that's right.
Yeah, I used to work with Caltrans for some traffic data, and I saw that it's pretty frequent to have problems in the data, particularly in the real-time data. There are different kind of reasons for causing the problem in the data set. Miscommunication and the malfunction of the sensors.
Yeah. Yeah, if you look at this.
Yeah, go ahead.
You look at this process, this what's currently in place, right? So let's see, this kind of control rule here they use to kind of QC data. So this rule is very kind of very rough, very simple. It doesn't capture all different type of error. So that's part of the reason we're doing this research. So make this more robust.
Okay, let's get back to the audience. Let's see if there's any question coming up from the audience.
But they are too nice,
It's pretty quiet. Maybe they're still digesting your content. Some of the, for those of you who are not familiar with deep learning, so some of the terms, including your presentation, probably are pretty strange or unfamiliar with.
Yeah, actually, this kind of simple application of the just the VAE model here is
some basic questions like what kind of tools did you use to perform this deep learning?
Oh, okay. We use the PyTorch pretty much. The PyTorch for deep learning is I think a lot of universities adopt the PyTorch. It's very convenient, also flexible. So you can go from research to application very easily using the PyTorch nowadays. So the good thing about the VAE basically they give you the kind of structured latent space where you go from one point to the other point, you kind of smooth, just like a smooth manifold. So you capture high level kind of feature there. In other words, it gives you better understanding of the data than just look at a particular data point or particular pixel in your original input space.
So you can get some information regarding the dimensions in the, in the latent state. So you like in your talk, you mentioned that there are 64. I believe that's 64, right?
Yeah, 64.
Yeah. So
right
you do have some knowledge or information regarding what are these 64 dimensions represent?
There are two. That's a very good question. There are two ways you can do that. One way would be, you just projecting your model to some kind of low dimension space you think would be easy to handle, and then you reconstruct it, right? So let's say when you train your model, if your model reconstruction is not very good somehow, right? So your latent space may be too small, right? So that's one way you can look at it. Another way is that you can encode your latent space as very large, but you make it sparse. You put a sparsity constraint on the latent space. That still give you kind of a, so to speak, high-level feature, a low dimension.
So how was
the number here?
Yeah.
How 64 been picked, right?
Yeah. Purely from a numerical performance perspective, or
there there's some kind of how to say this, some kind of intuition behind this. Basically, depending on how complex your input is, right? So for natural image, you probably need a more than 64. But for image we have here, for image we created based on the time sequence data. So those images much simple, much relatively simple, right? So we don't need a very high latent space here. So 64 here is, we tested some kind of variation of the latent space. 64 seemed to be work very well, work best for us.
So it's kind of selected with a little bit subjectivity.
Yeah, that's right.
And then you kind of use the PC. I think that's a principal component analysis, right?
Yeah, that's principal component analysis.
Down to 20. Again, 20 is kind of based on PC results.
Yeah, the over 90% of variance explained by 20 principal component. So that's the PCA basically easy for us to compute the distance there. That's kind of only purpose. Also the assumption here is your manifold have to be smooth enough, right? At the point where your PCA can kind of approximating your underlying manifold.
Now, so right now your methodology is mainly applied to the traffic volume data. I guess like this is a daily, hourly, maybe. Like a traffic volume.
Daily, yeah, traffic volume. Yeah.
And that's the total traffic volume. And maybe your methodology can be easily adapted to other type of problems.
Yeah. Definitely, it doesn't restricting to the traffic data. You apply to any kind of a time sequence data. In fact, we are doing an extension of the research on this one. We are doing, basically, we're looking for multiple stations, not single station, looking for the correlation among the station to get more interesting feature, to capture different kind of event going on. So that's something we're doing now.
So, okay. So, you plan to incorporate more data source. Here you have like a CCS and a VDS, and
yeah,
and there might also be other data.
Yeah, right now these two data sources is very easy to kind of to pair, right? To match. So we can do the kind of a cross validation from one source to another. So there are other sources could be factored into this as well, right? Depending on, let's say, your cellular data. But there are a lot of data kind of pre-processing and the fusion part need to be done to match them, right?
Yeah.
So the data fusion part will be the major task, basically. Yeah.
So this project is completed for Georgia DOT.
Yeah, it's completed, kind of completed. We finished the work, but we still kind of finalize everything. I think it's pretty much done. Yeah.
It looks very great.
Yeah.
Okay,
we'll
I'll get back to.
Yeah, go ahead.
Get back to the audience. I mean, the audience has been very quiet. Let's see. Any kind of question or like suggestions, comments? So I understand that Dr. Yang, you are teaching a course, a graduate level course on this on the related subject, like deep learning.
Yeah. Currently, I'm teaching two data related course. One is statistical learning and data mining, which offer in one semester, and this one is deep learning and engineering application course. The part of that I offer with another semester. Yeah, I mainly focus on take the state of art deep learning model and how can you apply that in different fields.
In your course is targeted towards students mainly in civil engineering or other?
No, it comes from every department. I got students from computer science and electrical engineering, mechanical engineering as well. Yeah. Of course, my students are attending this class. They are from
I saw a number of guests attended.
Yeah. It's kind of cross-disciplinary field. It doesn't restrict to any field. I mean.
But do like faculty members in other departments, like particularly the computer science, electrical engineering, offer similar courses?
They offer, not quite the same, but they looking at the different perspective, I believe. In my course, I'm looking at focus on the application part, right? How you can use those methodologies in your research. So especially in engineering application. So if those courses offered by computer science, their kind of a class project would be focusing on kind of a different application than what I offer. I offer here, all the students have to do a kind of term project, right? Their project have to be in their field, right? In the engineering field.
Yeah.
So pretty much, yeah. So we don't have any question from the audience?
Yeah, the audience has been really quiet. Well, I guess the presentation, your presentation is being recorded, and eventually it will be posted on the website of Color and with a link to YouTube. So, so the presentation will be available for the public through the YouTube, and I think the audience can have more time to digest the details. And I think and they can also reach you if they have any first questions.
Yeah, of course. Yeah.
Okay. If there's no any input or question from audience, please join me in thanking Dr. Yang for his presentation, and I think it kind of opens eyes for the potential application of the deep learning methodologies in the field of transportation engineering, particularly the traffic data analysis. And I hope you enjoy the rest of the week and have a great weekend. And we're going to have another seminar next Friday.
All right. Thank you.
Thank you.
Nice to meet you, Dr. Lu. I'll see you. Bye.
Bye-bye.